For a very long time, the CPU was the most important chip inside any computer. Everything ran through it. Every decision came from it. Every instruction started with it. The GPU was just a helper sitting on the side, waiting for the CPU to tell it what to do. The GPU was fast and powerful, but it had no brain of its own. It could not think. It could not decide anything. It just drew whatever the CPU told it to draw. This relationship between the two chips stayed the same for decades, and the whole world of computer graphics was built on top of it. But today, that relationship has changed completely. The GPU is no longer just a helper. It has become smart. It can think on its own, make its own decisions, and create images without waiting for the CPU to lead the way. This change happened because of one thing: artificial intelligence. NVIDIA built AI directly into their RTX graphics cards, and this changed everything about how images are made on your screen. The old way of making graphics, which is called native rendering, is slowly dying, and the CPU, which was once the boss of everything, has now become secondary. This article will explain exactly how this happened, step by step, from the very beginning to where we are today. It all starts with understanding how games and graphics worked for most of computing history. When you play any video game, two chips are doing all the work. The first is the CPU. The CPU is responsible for running the entire game world. It calculates where every object is located, simulates how things move and fall, controls how enemy characters behave, reads your inputs from the keyboard or controller, and manages every single system in the game all at the same time. It does all of this thinking continuously, many times every second. Once the CPU has figured out everything that is happening in the game world, it sends instructions to the second chip, the GPU. The GPU takes those instructions and draws the image on your screen. It is very good at this job because it has thousands of small cores all working at the same time, which allows it to draw millions of pixels very quickly. But here is the key point. The GPU only draws what the CPU tells it to draw. It does not make any decisions on its own. It receives instructions and follows them, nothing more. This process of the CPU giving instructions and the GPU following them is exactly what native rendering means. Every pixel on your screen was the direct result of a CPU instruction being carried out by the GPU. Every frame, every shadow, every reflection, every color, all of it started with the CPU. The GPU was just the executor. The CPU was the real creator of every image you ever saw. For a long time, the system worked really well. As CPUs got faster, game worlds became more complex and detailed. As GPUs got faster, those worlds could be drawn at higher resolutions and with more visual detail. Both chips improved together every few years, and gaming graphics kept getting better as a result. Players were satisfied, developers built great games, and the whole industry moved forward on the same basic foundation. But then a new challenge appeared. Players and developers started wanting graphics that did not just look good, they wanted graphics that looked genuinely real, like a photograph, like a movie. They wanted lighting that behaved exactly like real light behaves in the physical world. They wanted shadows that were soft and natural. They wanted reflections that were perfectly accurate. They wanted surfaces that looked exactly like the real materials they were supposed to represent. The problem was that achieving this level of realism using the traditional method was extremely difficult. Real light is very complicated. When a ray of light enters a room, it does not just hit one surface and stop. It bounces off the floor, reflects onto the ceiling, scatters through the curtains, bends through the glass window, and creates dozens of subtle effects in every corner of the room. Calculating all of this in real time using traditional math is an enormous amount of work. Even the most powerful hardware available could not do it fast enough to keep up with a running game. Because of this limitation, game developers spent years inventing clever tricks to fake realistic lighting without actually calculating it properly. They would pre-calculate the lighting for a scene and bake it into the textures so the GPU did not have to figure it out in real time. They used simple cube maps to create fake reflections. They used various shortcuts to make shadows look softer than they really were. These tricks were creative and they worked well enough for their time. But they always had limits. The lighting could not change dynamically. The reflections were not truly accurate. Everything still had a slightly fake quality that your brain could detect even if you could not explain exactly why. As hardware kept improving and player expectations kept rising, these old tricks started becoming inadequate. The gap between game graphics and true photorealism was still very large, and the traditional native rendering approach was not going to close that gap on its own. This is where NVIDIA stepped in with something completely new. In 2018, they launched their RTX series of graphics cards and introduced ray tracing to consumer gaming for the first time. Ray tracing is a method that actually simulates how real light travels and behaves in a scene. Instead of faking lighting with shortcuts, ray tracing shoots millions of virtual light rays into the scene and tracks exactly where each ray goes. what surfaces it hits, how it bounces, and how it affects the colors and brightness of everything around it. The results were genuinely stunning. Reflections became truly accurate. Shadows became soft and natural. Rooms felt properly lit in a way that had never been possible before in real-time gaming. However, ray tracing came with a serious problem. It required an enormous amount of calculation. The work involved in tracing millions of light rays in real time was so heavy that even expensive high-end graphics cards could barely run ray-traced games at smooth frame rates. The technology looked incredible, but it was almost too slow to be practical. NVIDIA needed to find a way to make ray tracing usable in real games. The solution NVIDIA came up with was not what anyone expected. Instead of making the GPU calculate faster, they used artificial intelligence to reduce how much calculation was needed in the first place. This technology was called DLSS, which stands for Deep Learning Supersampling. The approach was clever and simple at the same time. Instead of rendering the game at full resolution, which is very expensive, the GPU would render it at a lower resolution. Then, a trained AI model would take that low-resolution image and reconstruct it into a full-resolution image by intelligently filling in the missing detail. The AI had been trained on millions of high-quality images and had learned what sharp, detailed graphics look like. So it could look at a rough, blurry frame and produce a sharp, clean result that looked nearly as good as a fully rendered image. DLSS worked extremely well, performance improved dramatically, and ray tracing became practical for everyday gaming. But the truly important thing that DLSS did was prove a completely new idea, that AI could be trusted to decide what appears on your screen. Before DLSS, every pixel came from traditional calculation directed by the CPU. After DLSS, some pixels were created by AI running on the GPU. This was a brand new concept in graphics, and it opened the door to much bigger changes that were coming. Encouraged by the success of DLSS, NVIDIA pushed the idea of AI in graphics even further. With DLSS 3, they introduced frame generation. This technology went far beyond just upscaling images. Frame generation used AI to create completely new frames from scratch. The AI would look at real rendered frames, understand the motion and content of the scene, and then generate brand new in between frames that the GPU had never actually drawn in the traditional way. These AI-generated frames were inserted into the output alongside the real frames, making the game appear significantly smoother and faster. What made frame generation truly remarkable was the role of the CPU in this process. The answer is that the CPU had no role at all. Those AI-generated frames were never calculated by the CPU. The game engine never simulated them. The physics never ran for them. The CPU never sent a single instruction related to them. They appeared on screen purely and entirely because the AI running on the GPU decided what they should look like. This was a historic moment. For the entire history of gaming, every frame on screen had started its life as a CPU instruction. Now, for the first time, complete frames were being born inside the GPU through AI, with the CPU completely out of the picture. Building on this foundation, NVIDIA then introduced RTX neural shaders, and this is where the transformation became truly complete. A shader is a small program running on the GPU that decides how surfaces look. Every surface in a game has a shader working on it. Walls, floors, skin, metal, water, fabric, glass. The shader looks at the lighting around the surface and calculates what color and brightness it should be. Traditional shaders do this using strict mathematical formulas. Input the lighting conditions, run the math, output the color. Simple calculation happening millions of times every single frame. Neural shaders replace those mathematical formulas with trained AI models. Instead of calculating how a surface looks using math, the AI has already learned from vast amounts of real-world visual data how different materials behave under different lighting conditions. When it needs to figure out how something looks, it does not calculate. It uses what it has learned and produces the answer through intelligent inference. This is faster than math, and the visual results are more realistic than what formulas could ever achieve. With neural shaders running on the dedicated AI hardware inside RTX cards called tensor cores, visual effects that were previously too expensive to show in real-time games became completely practical. The soft, warm glow of light passing through human skin, the way velvet and silk catch light differently from each other, the complex shimmer of water moving under sunlight. All of these effects required very heavy math the traditional way, but a compact trained AI model handles them quickly and accurately. When you look at everything together, DLSS, frame generation, and neural shaders, the conclusion is very clear. The GPU no longer needs the CPU to guide it through every step of making an image. The CPU provides the basic scene information and then steps back. The GPU uses AI to fill in details, generate frames, and make intelligent visual decisions entirely on its own. Native Rendering, where every pixel came from CPU instructions, has been replaced by AI rendering, where the GPU creates images through intelligence and inference. The CPU still does important work. It runs the game simulation, handles physics, manages audio, and processes player inputs. But in the specific job of creating the image on your screen, it has become secondary. RTX AI has taken that job, and it is doing it better than the CPU ever could. The old system is dying, and a smarter, faster, more capable system has taken its place.